In this video I want to talk about the Euler Mascheroni constant, which is this gamma here. This is called the Euler Mascheroni constant, and its value is approximately 0.577. Then there are of course other digits. It's an interesting number and people still don't know whether this is an irrational number or not. As you can see, we have two definitions here. It can be written in different ways, but we will start from this definition. So the constant can be written in terms of an integral, and we will prove that this integral here is equal to this limit. This limit is an interesting one because if you plot visually what this means, this limit here can be represented by the following plot. So we can plot the function 1 over x. You can see a somewhat red area here and a blue area. The red area is the area under the curve 1 over x. Then we also plot the blue area, which represents these sums, which is almost the function 1 over x, but it is discrete. It is a discrete quantity. So this first rectangle here has a height equal to 1, between 1 and 2. Then this one here has a height equal to 1/2, and you get the idea. This is 1 over 3, and so on and so forth. The blue area contains the red area here, or purple, whatever it is. So this is the function 1 over x. And when we take a difference, so we are taking the difference between this sum here and this logarithm here. Remember that this logarithm can also be written as minus integral from 0 to n 1 over x dx. So you can see that these two have a very similar form. One is discrete and the other one is continuous. But we are talking about almost the same quantity, 1 over x here and 1 over k here. But the sum will produce a larger result because it contains the area of 1 over x, of the function 1 over x. So the difference between them, which is this area here in blue, this area here in blue, and all these areas, which become smaller and smaller as we go to infinity, all the sums of these blue areas will give us the Euler Mascheroni constant. So this is the visual representation of the Euler Mascheroni constant. It is an important quantity also in physics because it arises in quantum mechanics, in quantum field theory, and it is related to the gamma function. We might see that in a future video. Now we will prove that if we start from this integral, we can derive this limit. So we will prove this second equal sign. We will start from here. Let's do it below. So we have integral from 0 to infinity e to the minus x logarithm of x dx. By the way, this logarithm of x is the natural logarithm of x. Sometimes it is also written as ln x, natural logarithm. We can rewrite it in this way as limit as n goes to infinity of the integral from 0 to n of 1 minus x over n to the n minus 1 logarithm of x dx. Since as n grows larger, this function here will converge to the exponential. Now we make a substitution. The substitution that we are going to do here is 1 minus x over n equal to v. And if you substitute, you can rewrite the integral like this. It is the integral from 0 to 1 v to the n minus 1 logarithm of n times 1 minus v dv. Now this can be rewritten like this. We can use the properties of the logarithm. So the logarithm of n times 1 minus v is the logarithm of n plus the logarithm of 1 minus v. We can integrate the first term, so we get n log n integral from 0 to 1 v to the n minus 1 dv plus n times integral from 0 to 1 v to the n minus 1 logarithm of 1 minus v dv. And now what we are going to do, we are going to expand this function here, the logarithm, by using a series. And in particular, we can use a trick. We know that the function 1 over 1 minus v can be written as a geometric series. It is a series with k from 0 to infinity of v to the power k. Now, if we integrate both sides over v, we can rewrite this as the logarithm of 1 minus v equal to the series with k going from 0 to infinity of minus v to the power k plus 1 divided by k plus 1. Therefore, we can rewrite these two terms like this. I'm going to do it below. So this is equal to the first term is just log n after I perform this integration minus n integral from 0 to 1 series with k going from 0 to infinity v to the power n plus k divided by k plus 1 dv. Now remember that here we have to consider the limit as n goes to infinity. I did not write this part, limit as n goes to infinity. I have just considered this part to be implicit, but you have to remember that I should have considered here the limit as n goes to infinity. So after what we did, we can say that gamma, or minus gamma actually, is equal to the limit as n goes to infinity of this log n minus n integral from 0 to 1 sum over k from 0 to infinity v to the n plus k over k plus 1 dv. And now we can rewrite it as limit as n goes to infinity log n minus n sum over k from 0 to infinity 1 over. After I integrate, in this case I'm going to integrate this function. We get k plus 1 here, n plus k plus 1 equal to limit as n goes to infinity log n minus n. And now instead of rewriting the sum from 0 to infinity, I can rewrite it from 1 to infinity, and I have to change slightly this expression, and it is just 1 over k times k plus n. And now I'm going to rewrite this expression one more time. This can be written as 1 over n times 1 over k minus 1 over k plus n. It is easy to see that this quantity is equal to that one. So here we can rewrite this as limit as n goes to infinity log n minus sum over k from 1 to infinity 1 over k plus sum over k from 1 to infinity 1 over k plus n. And finally, you can see that this summation here starts at 1 over n plus 1, and then 1 over n plus 2, 1 over n plus m, dot dot dot. It goes on like that. This summation here contains also these terms, but it starts at 1. So we have 1 plus 1 half plus 1 third, and it also contains these terms. So I can rewrite this result like this. It's the limit as n goes to infinity of log n minus sum over k from 1 to n of 1 over k. And we have proved, therefore, the result that we wanted. We have proved that this here is equal to minus the Euler Mascheroni constant, and the Euler Mascheroni constant is equal to this integral here. So we have proved this result.